up till now, what we've done is define equilibrium for various reactions without anything real specific, but just looking at things reacting and writing equilibrium expressions. This week we're going to move into acid-base chemistry. I'm going to start with something that you're probably a little bit more comfortable with as far as how we define acids and bases. That's our Bronsted-Lowry acids and bases. We'll also define for you what hydrolysis is, what makes something a strong acid or a strong base or a weak acid or a weak base, and hopefully remind you of some of the things that you'll have memorized, committed to memory, really familiar with from last quarter, and then drag that forward. It will save you time and effort and energy and frustration if you are really comfortable with these things, with knowing which ones are strong, which ones are weak, etc. So let's take a look, shall we, with our definition of what is an acid or a base. So an acid is a proton donor, and a base is a proton acceptor. Last quarter you would have done reactions like this, where I don't know why it does that, we're just going to ignore it. Where you have like this acid, HCl, that you're going to mix with sodium hydroxide. And you probably would have done something like know what the concentration is of one, and you want to figure out what the concentration is of the other by the time you get to equilibrium. You use that information to figure out. So we get Na plus Cl minus plus a water. Hydrochloric acid is donating its hydrogen, so it's a proton donor, to my sodium hydroxide. So sodium hydroxide is my base. It's accepting a proton. And hydrogen chloride, or hydrochloric acid, is my acid, donating the proton. And I have two reactions written down here, and that's just to remind you, well, maybe remind you, that we don't actually have H+, the hydrogen ion, floating around in a beaker. What we actually have is this thing called H3O+, hydronium. That is what lives in our solutions when we're doing acid-base chemistry. And you'll see people represent them as in both ways. It's not that one is more wrong or right mathematically as much as it is that one is more physically correct than the other. And so what's happening here? I'm going to react a strong acid with a strong base, and I'm going to produce two waters from that. So I'm going to lose a hydrogen, donate it to here, which is going to leave me with H2O with my acid will become an H2O, and I'm forming H2O. My hydroxide is accepting a hydrogen to make two waters on this side. So this is the way you're more used to seeing it. And a fun little history tidbit for you. Bronsted-Lowry, they didn't actually much care for each other, but heck, they came up with this definition, apparently independently. I don't know enough about the history for why they didn't get along. I'm guessing it would be something to do with the competition for getting their name on how we define an acid or a base. It's kind of fun. You could go look that up. All right, so let's take a look at this. I want to know what is the base on the forward reaction for this. So what I want you to do is pause the video and come back and tell me what is the base. Okay, so who's accepting a proton? Let's take a look at what we have in the beginning. I'll just start on the far left. I have my ammonia, so NH3, and I look on the right side of the equation. What do I have? I have NH4, so it's gained. So I've gained a proton. If I'm gaining a proton, going from here to here, that makes my NH3 the base. It's all about the base, sorry. Okay, if I have a base, and the base has now gained a proton, that means I have an acid. So who is my acid? Well, the acid is going to be this water is going to donate, and we see over here, it becomes hydroxide. So on this side, what do I have? I have a strong base. Strong base. This would be a weak acid. H2O is definitely a weak acid, thankfully. And ammonia is going to be a weak base. And so why is that happening? Let's think a little bit about what our ammonia ion looks like. So we have, like, you know, here's our hydrogens. Can I do this? I can. Hey, look at that. And then, like, somewhere out here. So trigonal pyramidal. Probably can't tell from my drawing. But what we don't have there is this lone pair of electrons that exist. And that's part of the reason that everything is bent to give it this geometry, which these pictures do a much better job of doing than what I just drew by hand. So what's happening, I have my hydrogen here, which, by the way, when you see these pictures, they're always defined in terms of being white, and oxygen is always defined in terms of being red. Everything else is kind of iffy depending on the artist putting together the drawings. But I have this hydrogen hanging out here, and remember, water has like a couple lone pairs of electrons hanging out there. So when my hydrogen gets close to this lone pair, well, that proton is going to be attracted to that lone pair of electrons. And here I have it. My extra hydrogen pops off. Now what do I have left here? I have this strong acid, or strong base rather, sorry, because now on this side of the equation, it can accept a proton. So what does that tell me? Well, that tells me that in terms of this reaction, I'm not going to have very much hydroxide. I'm going to have more ammonia and less hydroxide. Why? Because I've created a strong base, so it's going to interact with that weak acid and reform my ammonia. But I still have this little bit of hydrogen dance going on there. Hydrolysis is simply anything reacting with water. This is, I think, the reaction I just accidentally wrote up on the last slide, where I have my HCl interacting with my water, and then I'm going to form my chlorine ion and my H3O plus, my hydronium. So let's just remind you that this is, we call this hydronium. We're just going to ignore that again, just ignoring it. Here's my hydronium. And we want to make sure that we always include these charges. So when we're dealing with our ionic expressions, make sure you have your charges on there, because as we progress through the quarter, you're going to see we're actually going to do something with that and do charge balancing. So it's going to save you frustration down the line, but it's also going to make things easier as you progress. But get in the habit so you keep things balanced. At any rate, so let's think in terms of a Kc. What would you expect the Kc to be on this? Would you expect it to be big, small, moderate, what? So pause and come back. Okay, first let's write our expression. What do we have? I have my Kc is going to be, let's see, products. So my H3O plus times my chlorine ion. They're both aqueous, so they're both going in there. Divided by, well, let's see what's going to go on the bottom. Well, my water is liquid phase, so it doesn't get included, but I do get my HCl down here. HCl. Cool. We can do something here. I can rename this thing. I can call this a Ka instead of a Kc. It means the same thing, but it lets me specifically identify that I'm working with an acid. So I've done a hydrolysis reaction by putting an acid into water, and I can write the equilibrium reaction. Now what about HCl? What do we think? Is it going to be a big Kc or a small Kc? Hopefully you can recall that HCl is a strong acid, and we define strong acids as dissociating pretty much completely and therefore I would expect my Kc to be much, much greater than 1. And in fact, what I have is you can look at this, here's my HCl ion. If I were to write this out, I would write it with this teeny tiny little backward arrow, because it's going to be more of a forward reaction with just a teeny tiny amount going back into my HCl. So if I put it in a beaker and I looked at it, I would see like maybe a small handful, if you will, out of 1,000 would still be HCl. Everything else is going to be either it's either going to be a chlorine ion or a hydronium ion. All right, let's talk about what's actually going on. And I think this is helpful for really picturing why you don't have just a hydrogen ion floating around in your solution. In your glass of water, before you drink it, there is a lot of motion going on between water molecules and neighboring oxygens and hydrogens. So we remember we have that lone pair in a water molecule. I have something like this. Okay, good. See, it stayed. I have something like this going on with just water. Well, what happens on its own is that because it's polar, I'm going to have my other water molecules kind of rotating so that the polar ends are favorably oriented towards one another. So with regular water, just tap water, what happens is I end up doing kind of like this do-si-do thing with my hydrogens, where they kind of bounce from one to the other perpetually. Thankfully, it's in a very small amount. We're going to get to a point where we're going to define how much of that happens. And so we're not consuming something that's harmful to us, either overly acidic or overly basic. In fact, water is defined as being neutral. So now if I add in here something where I have my one lone pair and then my 3 hydrogens, and these guys are going to interact now with my water molecules, and the same thing is going to happen, right? My polar ends are going to kind of rotate, and what happens, what you can see here is my bond lengths are changing, and this is in perpetual motion. It's constantly happening, and it's happening very, very fast. So as a bond length lengthens, so let's focus on, okay, the one that I've kind of marked here. This would be my original acid, say. That bond length lengthens long enough, well, all of a sudden this hydrogen here pops off and goes to that one, and then its bond length lengthens, and then eventually that one pops off, and now the hydrogen lives over here. It just keeps changing its address, and it's going to do that over and over again. So this very fast reaction of this hydrogen constantly shifting between all of my water molecules is just this constant state of motion that's happening in your cup, in your beaker. Let's see if I can get this to work. Will you work? There you go. And so you can see this actually happening in the graphic, where the hydrogen is bouncing, it's being attracted to the lone pair of electrons on the oxygen, and so there's this constant little shift going on in that scale. When I said it happens fast, the time scale is 10 to the negative 15 seconds. Okay, so this is not, I don't know that you can easily wrap your brain around how fast that is, but it's a very fast reaction. All right, so now what does it mean for something to be strong or weak? If I have a strong acid, do you think that it is really concentrated? That it fully donates its proton, sorry about that, it's dangerous, or it's pure? So pause and think about that. How do we define strong? Okay, so concentrated. Well, strong, you could have a strong acid and have like 0.003 molar. So strong acid doesn't have anything to do with concentration. Fully donate, so it'd be this one, fully donates its proton. So strong acid just means it's going to dissociate. Its hydrogen, its covalent bond between the hydrogen and the ion it's attached to, they dissociate and go their own ways and go flee about the vicinity of the beaker. Dangerous? Some of them are. Some of them aren't. If I have something really dilute, um, stomach acid, HCl, that lives in your belly, thankfully, it's not dangerous for the most part. Unless you get like an upset acid belly, then it might not be as dangerous as much as it is bothersome. Or pure. No, pure, definitely not, because what do? We put acids into water in order to get our reactions to go in most cases. So that's not the case. So it is indeed that we consider it to be fully donating its proton. So what makes something a weak acid? Do you think the proton donation reaction goes to completion? Proton donation reaction doesn't happen. Proton donation reaction has a small Kc, or it takes a long time to get to equilibrium. Pause and come back. Okay, well hopefully you came up with has a small Kc. So if I wrote, I have a hair tickling my nose, sorry about that. If I wrote an equilibrium reaction for that, and let's see, let's go like a Ka equals, I don't know, my products would be like, what do I want to make? H2O, why not? Let's actually write out a reaction. So if I do hydrolysis of HCl and water, sorry about that. HCl, my brain cannot decide what it wants to do. H2O is going to give me my Cl ions plus my hydronium, H3O plus. That's a strong acid, so I'm going to have a lot of product and very little reactant. What if I did something like HC, there we go, something like that. So some sort of carboxylic acid, and I put that in water. What am I going to get in the end there? I do get like this ion that looks like this, and plus H3O plus. There we go. So that says that this is going to dominate. I'm going to have a lot of that and very little of this. So my Kc is going to be very small. We'll just ignore that. If I look at it in terms of a picture depiction of what's going on, I can see if my chlorine ions are these guys, and here's my hydronium. So if I put HCl in a beaker, that's what I have going on here. I see I have a whole bunch of hydronium ions. And in fact, in this picture, I don't see anything that is an HCl. I just see my chlorine ions and my hydronium ions. So that means that all of my molecules are giving up a hydrogen, right? An H+. If I put hydrogen fluoride in my beaker of water, if you look at that, I have like one little small all alone fluorine. It's kind of sad. Only has itself to hang out with. So I made one hydronium ion and everything else just stays HF. So small dissociation, it's a weak acid. Now, fun fact, HF is a weak acid, but not really something that you want to stick your toes into. Very few labs like to work with HF because it is nasty, nasty stuff. Okay, so what happens when ionic compounds dissolve in water? Do you think they fully dissociate, partially dissociate, or do not dissociate? When an ionic compound dissociates in or dissolves in water, they completely dissociate. So that's going back to the fact that our water molecules are polar. So we have water with the hydrogen side and then the two electrons. Are we gonna, okay, good, it stayed this time. My two pairs of electrons like that. So whatever I put in there, I'm going to have something that's either going to be attracted to this partial positive charge or to this partial negative charge because water is polar. That eats away at my solid and just kind of pulls apart piece by piece all of my ionic bonds. And remember, those are electrostatic bonds, so the water kind of gets in there and detracts from that attraction, and so they fully dissociate in water. Now what about how many ions am I going to get from dissolving strontium hydroxide in water? I think I'm going to get 2, 3, 4, or 5. So let's take a look at this. What do I have? I'm going to do hydrolysis with strontium hydroxide. H2 plus H2O. What do I have? I have this solid that's like this strontium little sphere. There we go. What am I making that 2 plus? There we go. Sorry, I knew that was wrong. And then it's going to have these other minus, OH minus. My hydroxide ions floating around or attached next to. And I'm going to put that in my water, and they're going to interact with that water molecule, and in the end I'm going to have just the one strontium 2 plus floating around plus my OH minus, and I'm going to have two of those. So knowing what breaks apart and what doesn't is going to pay in dividends. So this is why knowing what your strong acids and bases are is very, very helpful, because you will know what bonds break and what bonds don't break. I am not going to break an oxygen-hydrogen bond in hydroxide. Hydroxide is a very stable bond. It's going to stay itself. Strontium, recognizing that that is a strong base, is going to help you recognize that they're going to break into 3 pieces. So do me a favor. That's a nice segue. Go ahead and make a list of the strong common acids and bases, and list 6 common soluble ionic compounds. And then come on back. So go ahead and make your list of your strong acids and bases and your ionic compounds that are strong bases. Okay, before we do that, because I'm going to give you a list, I want to take a look at the periodic table because it's actually quite helpful. And when I look at the periodic table, I can look at some of these things what's happening over here. What do I have here? Let's see, I know that hydrogen makes like an H plus. And if I remind myself, a lithium ion would also make a plus. And oh yeah. So these guys all have 1 electron in their valence shell. That's this first column, right? So hydrogen has 1 electron in its teeny tiny little 1s orbital, and everybody else are just kind of getting progressively bigger as we move down the periodic table, down this column here. So lithium has, it's not that much bigger than hydrogen, because let's see, we've just filled the 1s, so we're into our 2s shell. And come to find out, lithium isn't really going to do much for us as far as a base goes. But we do include that in our list of strong bases. So I can get LiOH, NaOH, the more common one, and potassium hydroxide. This one actually is not very soluble. This one here, again, not very soluble. Magnesium hydroxide. Now remember, this is going to have 2 valence electrons, so this is going to give us like 2 plus as far as my cations go. Magnesium, that base, that's something that you would put in like antacid. So if your stomach is upset, you would throw that in there and settle it down. And the reason why it's like that creamy color, the kind of milky looking, the milk of magnesium is what they call it, is because it's an actual suspension, because it doesn't dissociate that well. So that's why that works so well. But these 3, calcium, strontium, and barium, those also make good strong bases. And further on in the quarter, we will learn which ones don't dissociate as well as the others. Now, what about everything below that I've ignored? Like francium. So there's a fun video I'm going to post on Canvas that goes into how much fun it is to throw these different metals into water and some of that kind of exuberant energy that is released. And they do like this approximation of throwing francium in there and an entire boat blows up. It's made up from old footage. So it's not actually been done. But francium exists in such a small amount, and it's so extraordinarily reactive that they're just not things that we're going to work with. And then we also can get into things that are just flat out nasty. So the rubidium, cesium, and francium, these guys here, they would make strong bases, but we're just not going to work with them. Radium, yeah, we probably just don't even want to worry about that. And then when we come over to this side, let's see, what do we have? We're doing the opposite here. So this thing has, what do we have? We have 7 electrons in the valence shell. So I am going to form what? I'm going to form something that's like, go away, go away. Something that's going to be, it's going to, what? Fill its shell, or, yeah, it's going to fill its shell. So I get something that's like a 1 minus. So what do I get? I have HCl, HBr, HI. These here form my strong acids. And then we have some others that form, we have our nitric acid, sulfuric acid, and our perchloric. I can never remember that one. Perchloric acid. And I'll show you that on the next slide that you want to have memorized. But it is so much better, rather than memorizing, if you just have your handy dandy periodic table near you, you can use this. It's going to do it for me. Just to kind of, nope. Yeah, there we go. Just to kind of scribble on down. Okay, that was horrible. There we go. Scribble on down on the periodic table for what your strongs are. Then you don't have to memorize a darn thing. You can just let the periodic table be your guide. And there you go. As promised, there's the list that you need to know. So do yourself a favor and make sure that you're comfortable with that. And then we'll see you in the next video. Okay, stop.